All right, so today we're going to start our discussion, a new chapter, I guess, in this course, which is going to be about anomaly. But as usual, I'll start with a review of the previous lecture, standard model. And if there's something that through the review, if there are questions, please ask during the review. But just in advance to tell you a little bit about what we're going to do, we're going to have 3 lectures on anomaly. Anomalies are classical symmetries that do not survive quantum mechanics, right? Quantum mechanically, they're not respected. We've said already a few words about them, right? We've said that global anomalies are when you have, well, those are global symmetries are the only symmetries that exist, right? When they're anomalous, it's the measure, the action of the path integral is respecting the symmetry, of course, by definition of a symmetry. But it's the measure that fails to preserve it. And we're going to see that, and that's the issue of anomaly. Now, gauge invariance is not a symmetry. When we talk about anomaly, it doesn't make any sense to talk about anomaly for gauge invariance. What it means is the following. It means that if people talk about anomaly for gauge invariance, it means that they are checking the consistency of the theory. If your gauge theory is anomalous, it's nonsensical. In standard model of particle physics, we gauge the left-handed fermions, right? That is a particular invariance. If that was a classical transformation. If that transformation doesn't leave the path integral invariant, right? It doesn't make sense to talk about it, right? So consistency. This particular one, which is like gauging, say, left-handed fermions only, or left-handed stuff, is related to chiral anomaly, right? So consistency of standard model particle physics requires that we prove there is no chiral anomaly. Chiral anomaly cancels. So we'll talk about examples of this and simple cases. D equal 1. 1 plus 1 dimension is where everything is simple because representation theory of Lorentz group is simple. You guys remember how we did the representation theory of Lorentz group? And the general dimension. We didn't do much, I just advocated it. What's your starting point? Sorry? Group? Yeah, but like we went around all of that. There was at the end of the day, everything was we said it's all about the Dirac algebra, right? So we went through when we talked about 3 plus 1 dimensions, right? We took the group, we showed that like we studied the topological properties and all that. The little group came up when we discussed the representation theory of Poincaré, not Lorentz, right? That had to do with massless stuff. We're talking about Lorentz, right? The representation theory of Lorentz group, of course, is dimension dependent, but the master way of dealing with this was to write down the Dirac algebra, right? Find Dirac matrices. Then we had this thing we called gamma phi. You guys remember? It was useful in even dimensions. Even dimensions and odd dimensions were different, right? It was defined, d minus 1 comma 1, right? Actually, technically, this is not I. Thing is d over 2 minus 1. So it's I in 4 dimensions. In 2 dimensions, it's actually not there. But anyway, so this was a way that we construct. What's the next step? So we found this. What's the next step? The next step is this. You take the commutator of these guys. You call it sigma mu nu. I think there's I over 2. Oops, sorry. We constructed this matrix. What was the point of this matrix? This is the representation of J mu nu. Right? J mu nu, the Lorentz algebra was something specific. We basically, this gamma construction says that if you start with these matrices, You look at their commutators, you prove this and this relation. This relation implies Lorentz transformations. So you break it down to this, right? So every time you think about representation theory of fermions in various dimensions, the starting point should always be like, actually, the next step, do you remember what was the next step? In gamma 5 comes into play. So in even dimensions, 1 plus minus, well, in even dimension, the representation theory ended up being reducible, right? For the fermions, for Dirac fermions, right? So 1 plus minus gamma 5 over 2 were projections to two different parts. One of them was constructed gamma, and the other one was gamma bar. You also construct these using various things. So, and then the transformations are diagonal, right? So here we call these guys S lambdas, and these guys were S bar lambdas. Right? This was the representation theory in 4 dimensions, but the structure is general. That was a quick review, but we'll go through that. Sorry, I said all of this to say in 2 dimensions, this is super simple. That's why we focus on Chiral anomaly in 2 dimensions, right? All right, standard model of particle physics. That was our discussion last time. I'm going to summarize the 3 lectures at once. Standard model of particle physics is a renormalizable interacting 4-dimensional quantum field theory. As a gauge theory, the gauge group is SU3C for color, SU2 left for left-handed Majorana stuff, and Y1, UY, U1Y, Y for hypercharge, right? There's a gauge field here. There are 3 gauge fields here, 8 of them here. These are bosons, sorry. These are the gauge bosons. Then we said that the fermions are group them in 2 different ways, leptons and quarks. Quarks, the distinction was that leptons do not interact through strong force. So all the leptons are the trivial representation of SU3. These quarks are talking to each other through SU3 and the rest, SU2 and U1. Now, these 3 guys, so M is the generation thing. Yeah, we said we have 3 generations, right? Electron, up quarks, or EMs, UMs, and DMs, these 3 were Dirac fermions. So they had a pair of Majoranas. We broke them down into a pair of Majoranas, whereas neutrinos, there was just one Majorana, right? That we wrote as left-handed. All right, that was important. Okay. The representation theory is like this. The left-handed part of this, well, this guy is left-handed, and the left-handed part of this, they are packaged together. They interact together as a doublet of SU2 left. This is the representation theory. They are leptons, and their hypercharge is -half. The right-handed part of the fermion, of the electron or electrons, the 3 of them, electron, tau, and muon, are SU2 singlet, SU3 singlet, because they're leptons, and hypercharge -1. The quarks, the left-handed parts of up and down together, they transform as fundamental, and of SU3, doublet of SU2 left, and a 6 hypercharge. Then the right-handed side of the up and down are in these representations. Of course, they're trivial of SU2 because they're right-handed. Higgs was a complex scalar field that is color blind, so a singlet. It's doublet of SU2 because it's invented to break the SU2, and -half of the is this hypercharge. It breaks down SU2 left times U1Y to U electromagnetic 1, right? It's non-diagonal. How non-diagonal it is captured by this theta angle, theta of W. So let's recall how things are. G1, G2, and G3 are the gauge couplings for U1, SU2, and SU3. So G3, we're not going to touch it because it's not going to We're not gonna break it. G2 is the coupling of SU2 and G1 is the coupling of this guy. We define this angle as G1 over square root G12 plus G22. The electric charge is just G1, G2 over the square root. So this is the definition of electric charge, electromagnetic charge. There are 3 W bosons here, W mu A's, and then there's a B mu. This combinations became massive, right? We call them the W boson. It's a complex vector field. The neutral, so this is the charge current, the neutral one, and the A mu, there is this rotation matrix. Sorry, the third component, the B mu, we rotated them using this angle to the photon and Z mu. Good. This whole spontaneous symmetry breaking occurred because the complex scalar field Higgs acquired an expectation value. We use in unitary gauge where everything was simple. We set one of the components to 0. The other component is V, which has dimension of mass is 240 something GeV, plus the Higgs field, which is a real scalar once all the dust settles. Right? Any questions? This is the particle content of standard model particle physics. Here it is. Here are the masses. You know, things to keep in mind is that these guys are very, very heavy, right? You remember why? Because they come out of, their masses come out of electroweak, right? Photon is massless. Gluon, of course, massless. Higgs, what's the mass of the Higgs? Don't cheat, 125, yeah. All right, now we come to the leptons. Electron is half of MeV. Neutrinos, within standard model particle physics, they could not have mass. Why? Because you would have to have a right-handed neutrino, right? You would have to have a pair. You would have to have 2 Majoranas, and that would mess up everything. Change everything. In particular, one of the consequences, if there were massive, one of the consequences would have been that there is a new matrix, right? An analogous CKM matrix for leptons, there would have been with 3 generations. If there's 2 generations, it's a whole different story. And it's an interesting. Now I think you have all the tools to play around with, become a phenomenologist. I did not say that. All right, electron is half MeV. This is the way that the direction of mass is increasing. Muon is heavier and tau is really heavy. Here are the quarks. Their masses are basically, so the mass, yeah, looking at the masses are actually kind of interesting. Well, I think I trust they can do that. All right, so these are the interactions. Here are the matter fermions. Good. The only scalar in the game is this guy. And we said that it's kind of sketchy. Scalars are sketchy. Why? The quantum stability is kind of hard, right? Gauge theories, the nice thing about gauge theories was that under quantization, the gauge invariance principle was keeping everything intact, right? So gauge theories coupled to fermions were really nice. That's why I walked you guys through non-abelian gauge theory, right? But the scalars, if you recall, was messy because pretty much anything goes. Real scalar fields, they don't have much symmetry. And this gives us hell, as I mentioned at the end of the last lecture. Not within the standard model of particle physics. It becomes a fine-tuning. All right, so here are all the vertices that we have. Here are the Feynman diagrams. Vertices. Writing the propagators is straightforward. So here are strong vertices, right? Gluon interacts with quarks, not leptons, by definition. Gluons self-interact. And then these are the 2 diagrams of them. The theory confines in the infrared. So you end up with these bound states. What kind of bound states did we end up with? There were glue balls that were only strictly made of gluons. We also had QQ bar type, right? They were called mesons. So these are stuff that have a quark and antiquark and gluons that stick them together. And then we had like other stuff, 3 or more. They were called baryons, right? Neutrons and protons are examples of them. All right. All right, good. Now the electroweak is here. Let's start down here because it's easier. Actually, is it easier? Yeah, it is easier. So the photon interacts with anything that's electrically charged, right? This vertex is E, which was G1 sine theta weak, right? W's have a vertex with Z's and gammas, right? And W's have a vertex with four quadruple like quartic term. WW, 4 W's, 2 W's, 2 Z's, 2 W's, 2 gammas, 2 W's, Z gamma option, right? This just came out of just expanding the covariant derivative in representation theory of SU2 left. The interesting part was that, so these were the neutral currents, right? This part. Well, this is neutral current as well, right? Z interacts with fermions. But the interesting ones were these guys that we spent last lecture on. So here you have W boson, W plus minus, interacting with leptons and with quarks. These interactions were flavor diagonal, these lines. They turn neutrinos to electrons to neutrinos, right? Muons to neutrinos and taus to neutrinos, but their own types. When we say the electroweak, well, this already tells you that electroweak interactions often involve release of neutrinos, right? A lot of times, electroweak interactions involve releasing neutrinos. Absorbing neutrinos is very, very hard. You know why? They have very, very tiny cross section. They basically pass through everything. Now, importantly, the W boson will turn these UMs to DMs, but importantly, it's not, they're flavor changing. So it's not flavor diagonal. The issue is the following. You have this interaction to diagonalize. You also have the mass terms to diagonalize that were coming from Yukawa. Here, there was no mass term from muon. So you just use that diagonalization to render these guys diagonal. Here, you use it for mass eigenbasis. So these guys end up being flavor changing. Or if you diagonalize in this basis, what you end up with is flavor oscillations. Something is like propagating as U, all of a sudden it ends up being S, right? We don't want to do that. That's undesirable. But they are cool. It's just choice of basis, which is unphysical. These are field redefinitions, right? It's a change of variables inside an integral. CKM matrix was the matrix that told us about how this vertex works. And then there are Higgs self-interactions and the interaction of Higgs with fermions. The interaction of Higgs with fermions, the important thing you pointed out was that it's always proportional to MF. The coupling is MF over V. So if the fermion, the lighter the fermion, the more perturbative the interaction is. So for the most part, V was pretty large. It was 240 something. So for the most part, all the fermions were perturbative, except for one, which was top quark, which is around 170 GeV over 240 something. That's not a very small number. So it's not very perturbative, but anyway, it's all so hard to produce a lot of them because they're heavy. All right, so here's what I just said. The CKM matrix is coupling, is flavor changing, right? Yeah, I said that these 1 plus gamma 5s are to, well, you know that stuff. The CKM matrix comes from the fact that the unitary that we use to diagonalize the down quarks is not the same unitary that we use to diagonalize the up quarks. These U's themselves are unphysical, but their relative U dagger, UD is physical. Those are called the CKM matrix. Kibibo, someone, Kobayashi, someone, Masakawa or something. And the origin of it I just explained is that you cannot diagonalize these guys at the same time. So here's the standard form of the CKM matrix. There are various ways to parameterize them. Of course, it's unphysical, the basis we pick. But usually the way it's called the standard form of it, is formulated in terms of these angles, these Euler angles. All of these guys are real. These variables, these C and S's are sines and cosines of a bunch of angles. So all I need to report to you guys to describe the CKM matrix, which is unitary, right, are these Euler angles, and there's only one phase here, theta 1, 3. That I can also. So everything is real except for this phase. So I'm just going to report the phase as well. Good. Now, these are called mixing angles because they involve mixing of flavors. Experimentally, oddly enough, we found that theta 1, 3 is much larger, much smaller than theta 2, 3, smaller than theta 1, 2. All smaller than 1. So the matrix is very close to identity. There is very little flavor changing in standard particle physics as we've observed nature. Notice that these variables are things that we have literally deduced from experiments. There's no explanation of these variables. These are parameters that go into the building of standard particle physics. So for some unknown reason, fermion flavor changing physics is suppressed. We said that the CP symmetry, otherwise known as T symmetry, time reversal, is preserved if the CKM matrix is real, can be made real, sorry. Yeah, there's no CKM matrix for leptons, and the lepton double boson interaction is proportional to G2. That's usually called weak universality. Any questions? All right, beyond standard model, what is not explained? I mentioned 3 things. Dark matter, all the matter that we just described, the matter energy that we just described, is only 5% of what is the matter energy density of the universe. 26% of it we know is ordinary matter, but it interacts, but it's not standard model. So we gotta explain that somehow. That already tells us we gotta push beyond standard model. It's a very serious problem. Neutrino oscillations, they care. Neutrino oscillations mean that the same way that, like I said, that remember what we did, we're comparing the flavor changing physics of the flavor changing physics interaction of W boson with quarks and leptons, right? Neutrinos, we took them to be massless, so we just used up our unit Fielder definitions to diagonalize in the interaction, to make the interaction of W with leptons flavor preserving, flavor diagonal. We did the same thing. We diagonalized the quarks and masses, so we ended up with a CK matrix, which was flavor changing. Now, what happens is that if we got, for some reason, the physics of neutrino mass wrong, if there was mass for neutrinos, then because we diagonalized in the interaction basis with neutrinos, with W, we would see neutrinos as they propagate, they're not in energy eigenstate, mass energy eigenstate, so they'll just fluctuate, they will oscillate. Right? That's called neutrino oscillation. It's been observed. And within the standard model of particle physics, or going beyond it with minimal assumptions, it's natural to attribute that to a mass term for fermions. But that would imply that the model changes significantly, right? We don't really know the mass of neutrinos quite yet. Let's see, I have a line here. Yeah, no, we We don't know the mass of neutrinos. We have bounds on their sum of the masses. It's hard to distinguish their masses, and that is going to be the physics of your generation, guys. We did our part. I'm on my way out. Neutrino oscillations are unsolved. There is another issue is matter-antimatter symmetry. Now, matter-antimatter symmetry is not necessarily a problem. It's a different type of problem. The problem is that the theory is fully consistent with, so the theory tells you about the dynamics, interactions. What state you're in is a statement about how much matter versus antimatter you have, right? The state of the universe happens to be in one that has tons more matter than antimatter, and we don't understand why. This is not a problem for standard model particle physics per se. It's standard model for particle physics, right? It's called baryon and asymmetry. It is a problem for applying standard model to cosmology because you have to explain it. All right, that's good. Here is the table. Here are the values. Yeah, we said all of this. It's super interesting that when I took standard model as a course, the Higgs mass was not known because it wasn't discovered yet. Yeah. All right. Two of the things here were not known. Well, anyway. Okay, any questions here before we move on?
Is there any reason for the number of parameters is 19 in the standard model? Just a matter.
It's just the model we built. Yeah, that's not explainable at the moment, right? Unless you put this in a larger. Sure. There are other issues with standard model. Yeah.
Is there a particular reason for 3 generations, or is that just nominal?
We do not know at all. There's absolutely no understanding of that. Any other questions? Problems? Standard model. All right. Oh, I said one more thing that I didn't put in here. Well, okay, no, we're gonna get to. I mentioned that the a very serious problem is hierarchy problem. A scalar field that has a fixed mass is relevant. So if you're seeing the mass to be whatever we're seeing it to be 100 something, it means that deep in the UV, this was teeny tiny. It had to be fine-tuned absurdly well. The reason is that the fact that it's relevant has to do with the fact that, well, you know, like fermions run in the loop, right? And particles run in the loop, right? Particles and antiparticles run in the loop, and they all contribute to the mass, right? So there's a fine tuning. It's called hierarchy problem. It's pretty darn serious. Another way of saying that is that it's unknown why gravity is so much weaker. Why is that a formulation of the same problem? Gravity is the only indication of a cutoff of the theory. Standard model is renormalizable, right? So it works pretty well. The only place where we have to stop trusting it if we don't take it literally is Planck scale, right? That's the scale where gravity becomes strong. Electroweak becomes strong, or all the other forces become strong at energies way below that. Why is gravity so weak? That's a question. By the way, all right, so we're going to change here and talk about chiral symmetry today. To motivate this and connect it to the discussion of standard model, I want to remind you that in standard model, we had SU2 left gauge invariance. We took left-handed Majoranas, right? So remember that these guys expressed as 4 Lorentz vectors in 4 component things could be written as left-handed electron And here's this right-handed thing that we just cooked up so that it becomes a Majorana, right? It's its own antiparticle. And here is the neutrino left-handed. We put them in doublets, SU2 doublets, because we were curious and wanted to understand SU2 symmetry breaking. But that doesn't matter. Let's work with the space-time transformations, right? So these are 4 vectors. The gauge transformation of a Majorana, if you have some gauge, some charge generator, TA, is like this. This is transforming the P left. Let's say I couple only the left-handed stuff. Well, I have a Majorana. I have 2 degrees of freedom, right? So the left is transforming using TA. The right-handed side of the left-handed Majorana will transform with TA star. Right? We saw this explicitly. I expanded the gauge covariant derivative. We saw exactly how this works, right? So this is a transformation. And we checked that this is, well, by construction, we constructed an action that was, this was this classically invariant under this. But the question, does this survive quantizations? This is a serious issue because gauge transformations cannot be anomalous. Chiral anomaly must vanish. Or we just haven't, our theory is nonsense. What does it mean if chiral anomaly exists? It means that, so what goes, well, we'll see. What was the consequence? One of the physical consequences of gauge invariance was what? What was the simplest consequence of gauge invariance that in the world around us? Photons are massless, but something even more obvious. Ward identities, what do they tell you? Charge is conserved. Electric charge is conserved, right? That's a very obvious implication. So what happens is that you end up with charge that's not conserved. This is, yeah. These charges for electromagnetism or gauge theories, if you recall, we integrate them over these like codimension 1 surfaces to find them, right? But that's just nonsensical. It's not a gauge theory anymore. Because these are this is invariance, right? All right. Consider QED coupled to massless fermions in 4 dimensions. So I said that there's some chiral anomaly we have to calculate in standard model. I want to go down to a simpler example, discuss it in detail, and go back up. So QED coupled to massless fermions in 4 dimensions, or any even dimension is a simple case. Here's the action. Here's the Lagrangian, right? This is the representation theory. This is my gamma 5. I erased it already. Let's block diagonal. Remember, our fermions were transforming separately here and here because the Lorentz transformations were blocked out, right? And gamma 5 is identity minus identity, so that identity plus minus gamma 5 over 2 is a projection to up and down, right? All right. Now, what we have, these are vectors, right? So our fermion is this is E left, and this is E right, for example, right? When we talk about gauge transformation, this 4 vector, if I can gauge the left-handed side and the right-handed side separately. I can choose to gauge only the left-handed side or only the right-handed side, as we did, right? In principle, I can view a general gauge transformation as vector transformations, the ones that this is the same as this. They gauge the left and the right-handed side the same way. And then the axial one that gauge them in this opposite way by some gamma 5. Right? So this does it diagonally the same way for both. This guy does it asymmetrically. This is called vector transformation. This is axial, just to set the notation. I'm talking about massless QED, right? Not a fancy theory, just massless QED. When we talked about U1 gauge symmetry in 3 plus 1 dimensions, my gauge transformations were actually two. There were two of them. Well, we had a mass, so it was actually distorted, but good. There are two conserved currents. There is the vector current this way, psi bar, gamma, mu, psi. What was psi bar? Psi gamma 0. And then J mu axial, which has this gamma 5 in the middle. Hopefully you get the picture. This is diagonal. This is like 1 minus 1. With blocks, there's a relative sign difference. If you have a mass term, classical mass term, the vector one is preserved. The axial one is not. So here's a contribution from the axial one is explicitly broken. The axial gauge transformations are not gauge transformations. So massive QED in 3 plus 1 dimensions has only these currents, right? These are just not there. Once you make it massless, there's two copies, right? This is an explicit violation of classical symmetry or invariance. Chiral anomaly is a quantum correction to both sides of this. Right? So this is a classical violation, master. But quantum mechanically, there could be a term appearing here, term appearing here. So in particular, we're going to be interested in the case that because we want to gauge the left-handed fermions alone, we're going to be interested, and that would only make sense if we show that this chiral anomaly vanishes. Is it clear what we're going to do? So I'm going to do this in 1 plus 1 dimensions to simplify our lives. Let's go back to our rules. We have to construct the representation theory Lorentz group. Oops, I don't know what I was doing there. The starting point is the Clifford algebra or Dirac algebra. You have to find matrices that satisfy this relation. 2 by 2 matrices. Here they are. Your gamma 5 is gamma 0, gamma 1. It's I to the power of d minus 2 minus 1. So it's just this. Not surprising, right? Gamma 5 is just 1 minus 1. Your chiral modes are up and down, side plus, side minus. Why do you call them plus minus? These are the eigenvalues of gamma 5. Yeah. These are the eigenspaces of the gamma 5. The projection only has one and 0. All right, so here it is. So expanded in this form, the Lagrangian looks like this is a covariant theory, right? These are covariant derivatives. So I'll put this is a covariant derivative. D0 plus D1, D0 minus D1, psi naught, psi dagger. I've just expanded both gamma mu and gamma 0 in there. I've just put everything, and as matrices, this is what it is. If the electric charge is 0, the theory is free fermions in 1 plus 1 dimensions. The equations of motion are these. Psi plus and psi minus are left-handed and right-handed decoupled modes, right? They are just two copies of this chiral theory. The point is that you could gauge only one of them. You could choose to gauge only one of them. Is that clear? That's what we're doing. We want to do it in a chiral way. All right. These are the relation, left-handed and right-handed. There's symmetry. What is the symmetry? What's the conserved current? The current, the number current of these fermions are separately conserved. So these are the number of fermions because they don't, there's a free theory, non-interacting, right? Here are the conserved currents, and these are the conservation laws. These are the vector and axial currents, and they're just numbers. They count for you how many of these particles and that particle you have. If you are curious about the vector and axial parts, these are 2x2 matrices. This is literally e to the power of I alpha x, e to I alpha x, so diagonal. This is e to the power of I alpha x, e to the power of minus I alpha x. Good. That's gamma 5 and gamma 5 and no gamma 5. Diagonal and the vector and axial. Is it clear? Said differently, the symmetry acting on spinners, every symmetry acting on spinners could be split into the vector part and the axial part. The vector part treats the left and right-handed modes the same, and the axial part treats them the opposite way. I said this before, there can't exist any axial anomaly, or our theory is nonsensical. All right, axial anomaly in QED 2-dimensional QED. Of course, you wouldn't be surprised. To calculate this, we're gonna do Feynman diagrams at one loop. But the good news is that we don't need to do any new integrals. We recycle all the old integrals. The thing we're gonna focus on is the vacuum, is the vacuum polarization. When fermion, anti-fermion, electron, anti-positron run in the loop as a one loop contribution to the propagator of the photon. Here is pi q, right? This is the expression I wrote down. We wrote this down, we wrote down this integral explicitly, and we can directly apply to d equal to y because we were doing dim reg. That was the advantage of it, right? Dim reg just gives you right away the answer in all dimensions. Here's the expression. Now, there's something special about the 1 + 1 dimensions. When you put d equal 2 here, you could, this expression is non-singular. There are no divergences. You could have guessed that. You knew that in lower dimensions, divergences are less bad. If you remember, we said in the past that 1 + 1 dimensional theories, often, by just dimension counting, were becoming super normalizable. These were setups that a lot of things were becoming finite. We're not even blowing up. This is an example of it. All right, so here's what you write down. Pi mu q is this. Now, interestingly, you realize that when the fermion is massless, right? M of psi is 0. This x, 1 minus x, and this x, 1 minus x, they cancel. You could do the integral explicitly. It all comes out, and you get this very, very simple answer. This corresponds to the amputated diagram like this, right? So this is E2 over pi, eta mu nu minus q mu q nu q over q2. This is C equal 1 gauge. Right? This implies a photon mass. Hopefully you remember why. But we said that gauge invariance, in the past we said that gauge invariance does not allow photon to be massive. We went around and looked at it, and we said there are exceptions to it. What was the exception we discussed? Spontaneous symmetry wrecking. What was the issue? And when we wrote down, we had to keep ward identities, right? And we looked at pi mu nu q. There was an assumption about the poles of this. We assumed that there were no poles. This was all, like there were no poles coming, right? There were no poles in that, which is the case if you have massive particles running in the loop. From that, we deduced that ward identities imply that photon mass should be zero. But when you have massless modes around, as you would get in spontaneous symmetry wrecking, or here where we're putting electron, the mass of electron by hand to zero, it's possible to end up with massive photons. So 1 + 1 dimensional QED actually has a massive photon. What's really fun about it is that, okay, so we calculate the photon mass is E²/pi. This is that one loop, but Schrödinger proved that it's actually fully non-perturbative. The theory is like super normalizable. So it's trickier than you can't just say those words and say, voila, this is the answer. You have to solve the model, but he did. And this is the photon mass, which comes out really nicely. It's just a number. It's E²/pi.
If the photons are mass, then it should be a short range interaction, right? We won't get the information around it.
Yeah, that's fine. Yeah. The same way as spontaneous symmetry wrecking. Same story as spontaneous symmetry wrecking. So the issue has to do with the okay, I'm not going to explain. The structure of divergence in 1 + 1 dimensions is very different. There can't be spontaneous symmetry wrecking in 1 + 1 dimensions. There's a theorem. You can't do that. It's called Coleman-Mermin-Wagner theorem. It's only in higher than 1 + 1. And it has to do with the structure of the correlation functions. Massless modes will end up being having log divergence in their 2-point function. So massless modes are not normalized. Anyway, I'm not they don't create normalizable vectors from the vacuum. Anyway, I said all of this. Here we have massless modes running in the loop, right? So everything is fine. All right. Why did I calculate the vacuum polarization? Because there is a very quick way to calculate the derivative of the axial and vector currents just from the calculation we did. How? Well, what is this thing that we want to calculate? If you take the current and go to momentum space, that is just precisely at one loop, it's just this diagram. We already had this part of it. This is just a background gauge field. So it's minus IE minus 1 I pi mu nu q, which was the amputated diagram, right? A nu q, which is this guy. All right. You just put them next to each other. This is the answer. You Fourier transform it. You end up with, whoops, the right Lorentz indices. You end up with ward identity for the vertical part, for the vector part. So the vector current is conserved at one loop and all order, because I told you it's exact. However, well, now we have to calculate the axial anomaly. Are there any questions? Is this clear? Or am I going through this too fast? So what does it, okay. Now I want to calculate the axial anomaly. Luckily, we could recycle the same calculation. This step is precisely why I went down to 1 + 1, or people usually go down to 1 + 1. It's because in 1 + 1, you have this relation. You could just check them explicitly. from the gamma matrices. So you can write down the word identity for the axial current related to the word identity for the vector current. You write it down. There's basically this epsilon mu nu contraction that sits outside. Here's the form of it. You calculate the derivative. This value comes out. Minus E of 2 pi epsilon mu nu F mu nu identity 1. Axial anomaly is there is axial anomaly in D plus 1 in 1 plus 1 dimensions. No, massless QED. This is pretty bad. The amount by which this is violent, this is the quantum correction, right? We said that if there was mass, there would be a mass term, right? This whole calculation goes through if there was a, well, anyway, I'm not going to over explain, but this is a quantum correction. Another way of saying this, as I'll explain, I've said in the past, but I'll explain it in the remaining time, is there exists no regulator that can preserve both of these guys. So the charge associated to the axial current is not conserved. Any questions? What I want you guys to actually, if you remember, we had very similar expressions in spontaneous symmetry working we wrote down. It was the same calculation. It was the same massless modes running in the loop. It exactly came out the same way. This expression is literally copy paste from the same. Right. What I'm gonna do in the remainder of this 15 minutes that remains is to. This was a calculation we did in 1 plus 1 dimensions by looking at one loop, and I just claimed its exactness. This. I've said in the past many times that the anomalies have to do with the failure of the measure, the absence of a regulator that preserves the transformations, right? The fact that the measure must violate, right? So we're going to see that now. What we're going to do is that we're going to look at the path integral measure. We're going to evaluate it. We're going to try to regulate it, fail miserably, and see this term pops up. We'll explicitly regenerate this term by going through a path integral analysis. Now, of course, at one step, catch me when I do it, I'll make an approximation that would correspond to one loop, but you'll hopefully catch it. All right, is it clear? So this is called Fujikawa method. There is yet another way of thinking about anomaly. For the case of global symmetries, for the gauge transformation is nonsense, right? We said that symmetries, honest to goodness symmetries in quantum mechanics were represented in the Hilbert space using unitary and anti-unitaries. Anomalies tell you about the failure. So when you have anomaly, your transformation, there exists a way of transfer. There's some operator that linear operator that does your transformation in the Hilbert space, but it's no longer unitary. This failure of the transformation to be unitary on the Hilbert space. For gauge transformation, it just doesn't make any sense. For global transformation, that's what it is. Good. Fujikawa was the person who sorted this out, and it's called Fujikawa method after him. The story I'm gonna tell you is very specific to this chiral anomaly, right? But same method applies for any anomaly. Same principle, right? Like it's a very, very simple setup where I could be very explicit about everything, right? But Fujikawa method is fully general. Any anomaly, global, whatever. All right. So we had the axial transformation this way. Remember that in the path integral psi and psi bar, we treated them as independent functions and we path integrated them over them separately. It came from the fact that in the path integral formulation, the fermion path integral formulation corresponds to phase space path integral. Psi and psi bar were conjugates, momentum conjugates of each other. In the case of scalar field or a bunch of other subs, for in the case of scalar field, we could explicitly do the path integral over the momentum conjugate, right? Why? Do you remember? It's Hamiltonian is p squared. So that p squared part you could explicitly do is a Gaussian. We did that. All right. But that's an analogy. This is closer in analogy. This is closer to complex scalar field. Anyway. All right. So here's the action. Under the axial transformation, it transforms in this following form. If there's a mass term, there is this bit. This is an explicit violation. Right? There's a term that will proportional to alpha as that will be bad, right? This is explicit violation. Let's ignore that for now. So let's set m equals 0. The other term that comes up is this term. This cancels out. Why? Because you do integration by parts, put del mu over alpha, that is 0 for gauge transformations. Right? So the action is invariant, of course. That was a sanity check. Now we want to study the measure, path integral measure, path integral over psi and psi bar. Actually, what I'm going to say is like, for a big part in general, at some point you'll see when I go to 2 dimensions. All right. What's the meaning of these path integrals? These are integrals over space of functions. If my space was, for some reason, let's say a cylinder or something like compact or nice, right? Then I could have Fourier transformed. And if the solutions to my equations of motion were labeled by an integer or something, like a Fourier transform, right? It would be, I would be, these modes are decoupled. I would be performing an integral for each of these modes, right? That's what it would mean. How do I construct such independence? Well, I look at the equation of motion. This is the same story. I look at the equation of motion, which is the Dirac equation. I look at the eigenfunctions of the Dirac operator. Lambda m's. Now, so these are the eigenvalues. These are lambda phi m's are the eigenfunctions of the Dirac function, right? So I have the left and right, or if you wish, I have the phi bar analog as well, right? I have these guys. Whoops. No, actually, wait. Yeah, that's right. Now, an arbitrary function, because these are solutions to the equations of motion, I can diagonalize them as well, right? An arbitrary function could be expanded in terms of these guys. This is the Fourier transform I was talking about, right? So I'm just expanding an arbitrary function in the base, and this is basis. This is a complete basis for the space of functions. To do, these are your basis vectors, right? To do a path integral, it means that you have to integrate over each AM separately. So your path integral measure is a multiplication of an integral over dA prime m, that's the expansion of psi bar, and there's an integral for each of these guys. But importantly, these are Grossman integrals, because these are fermions, right? These were just solutions to the equations of motion, so I have to take these guys to be Grossmanian. Do you remember the Grossman integrals? Did we do them? Yeah, we did. Good. It would be a serious failure if we're at this point in QFT2 we haven't done a single Grossman variable. All right, so this is what it is. All right, So what happens is that under the axial transformation, there will be a Jacobian for the transformation, J minus 2. We're going to calculate this J minus 2. This J is not to be confused with currents. I apologize. It's just J for Jacobian. Now, if this comes out to be independent of the field, what's the interpretation of it? It is invariant. It's just a scaling of the whole thing, but it's just meaningless, right? Because the overall value of the partition function is meaningless. We saw that in what? In QED. Remember? In QED, when we were doing gauge fixing in Faddeev-Popov, we had this Jacobian. But the Jacobian the determinant of the Jacobian, which is what we're dealing with, turned out to be independent of the field. So we just threw it out and say gauge invariance is all good. When we did the gauge fixing for non-abelian gauge theories, what came out was dependent on the background gauge field, right? So what it meant was that gauge theory without that term was nonsensical, right? We exponentiated that term as ghosts, put them back in the action. Now the full theory had the ghosts. It didn't make any sense to just ignore them. In that case, probabilities were not adding up to 1. It is horrible. It's expected. When you insist things that are not unitaries to become unitary, you treat things that are not unitary as unitaries, your probabilities are not going to add up to 1. That's the sense in which, the theory is nonsensical. It's not just some charge is unconserved or something. Your probabilities don't add up. So the theory is horribly sick. For gauge effects, right? So here's the Jacobian we're going to calculate. So how are we going to calculate this? Well, what is AM? AM, you just, I have made these solutions to the equations of motion diagonal, right? Orthonormal, right? So I just calculate AM by integrating psi against phi bar of M. Psi transforms this way under a gauge transformation. That means that AM transforms in this way. So AM goes to AM plus this extra term, which depends on the gauge, right? There's gamma 5 in here. There's psi x in here that I'm going to expand again as sum over n a n c n x. And this is what it is. So packaged this way. Wait a second. How do I want to say this? This is wait, what is that? There's no CN in there.
It should be ANCN, right?
Sorry. Phi n. Also, yeah. Right. So the sorry about the typo. This is CMN, right? These are the matrix elements of this thing that's going to become the Jacobian. It's just an integral over space. These involve an integral over space, time, right? A phi m bar, alpha of x, gamma 5, phi n x. All right. So it's a matrix. I'm multiplying pi. My measure is product of m of AMs. So this becomes product of I can treat this as a matrix. So I'm dealing with this Jacobian I'm talking about, the determinant of 1 plus c as a matrix, CMN. I can write it as exponential of trace of log of 1 plus c, which is approximately e to the power of trace of c.
Is this
Yeah, this is that's precisely where I do a one loop expansion. All I need to calculate at this level is just trace of C. So what is C? Here it is. I just have to calculate its trace. Yeah, that's right. That's right. Trace means what? This means trace means sum over n of phi n's, right? Because this is the matrix Mn, M and N. I just have to sum over N, N, N. Here it is. If this term, okay, very good. Is this clear? At this point, you might think that, oh, this looks like it has no field in it. So what is this anomaly that we're talking about? Why is this not independent of field? The point is that these phi n's are solutions to the Dirac equation where the covariant derivative had the field in it. So these phi n indirectly depend on the field, A mu. We're gonna play a trick to see that. This sum over n is infinite and needs to be regulated, like every other trace in quantum field theory. All right, so this is what we want to regulate. We're going to introduce e to minus lambda n squared over m squared inside the sum. These lambda n's are the eigenvalues. That are negative. I'll show that in a second. Sorry, lambda n squared is negative. They're imaginary. This suppresses the high modes, the large large n's, right? The ones that the larger the eigenvalue of the Dirac operator is, the more suppressed it would be. The imaginary part of it, right? All right. Is the regulator clear? Okay. This lambda n, you could think of it as e to the power of I Dirac operator squared over m squared, right? That's just what it is. So I can write it elegantly in this form. That makes it explicit that this depends on the field. Now, all I need to do at the end is just expand this ID slash squared. This is a very, very useful identity that somehow we've managed to avoid up until now. This is the Dirac operator squared. This is minus gamma mu d mu, the covariant derivatives. You could package it this way, right, in terms of gamma mu, gamma nu. Hopefully you remember, I said a couple of times today, that this is just a representation of J mu nu, right? So you can package it this way. And yeah, actually one last step. This last step is for you guys to figure out why I package this as F mu nu. Yeah. I use the anti-symmetry to package it that way. Very good. So here's the expression. I'm going to expand it in small this value, because m going to infinity this is 0. So I'm going to expand it in large M squared. This is the first order term. This is the second order term. M squared. Yeah. All right. Do I need to say something? In D equal 2, the trace of gamma 5 is 0. And we have this relation. I'm running out of time. Let me just say this quickly. So you just use these two relations to package it this way. You calculate the log of J. And finally, you find that the Jacobian in this one loop approximation I did is just exponential of I over 2 pi integral of alpha of x, which is the gauge, epsilon mu nu, F mu nu. If you go back to the derivation of word identity, tells you that as an operator equation, you have this relation. Let me just get rid of this so that you guys don't get confused. As an operator relation, you have this inside the path integral. This is precisely what we had before as the chiral anomaly. Okay. So what did we do? Any questions? What we did was that we calculated chiral anomaly for massless 1+1 dimensional QED, right? We found that there's an anomaly term at one loop using just Feynman diagram by looking at the vacuum polarization, playing some tricks for gamma matrices that hold in 1+1D. Alternatively, we use a path integral and showed that this regulator we picked does not cannot preserve both of them. But in fact, it's any regulator. Because if there was another regulator, we could just repeated this calculation, would have gotten something else that would have been a contradiction, right? None of the regulators will keep this symmetry. So what does this mean?
In 1+1 dimensions, QED is not very.
QED is fully well defined.
No, because has an all effect, so.
Massless
Oh, that's
1+1 dimensional QED only has the diagonal gauge invariance. You can't gauge it chirally. You can't take psi plus and view that as a left-handed gauge theory. Chiral gauge theory in 1+1 dimensional is anomalous. That's what it means. Whereas the full gauge theory, remember what we here, we're not discussing JV. That guy comes out clean. Gauge invariance in 1+1D is sensible. The diagonal part, not separating the axial versus not. You see, this is important. For massless case, you have the option of gauging them separate. That was the whole point. All right. Any last questions? So in summary, what did we do today? We started with Stanmol, we reviewed and said we have chiral, we have gauge theories that are we're gauging only left-handed part. So the chiral gauge invariance, we have to make sure that it's non-anomalous. We didn't calculate this in 3+1. We did it in 1+1, and we showed that for massless, well, for gauging the gauge invariance is an issue. So next lecture, we're going to go back to 4D, and we're going to calculate this for standard model, and it's going to cancel all the stuff that we put in the standard model. They just happen to cancel. These anomalies happen to cancel, and it's consistent. It didn't have to be that the case. So Samuel comes out clean. All right. Any questions? That's a very non-trivial calculation. Thank you.